Let me remind you about the class test on Tuesday. The details of this class test will be shared uh, in due time. Uh, so let me, before starting today's tutorial class, let me take some time to complete whatever I was teaching on thermistor. Let me complete that first, then we will be taking the, uh, trying to solve the tutorial problems there.
Hello, sir.
Yes,
Sir, what will be the pattern of the test on Tuesday?
it would be some, when what we would say that it is not tick mark or just ABCD type, and completely it will not be also completely problems. Some problems should be there where you need to solve and upload. We like to see how did you do it, and also some short questions where you need to explain the conceptions. Okay? Is it okay?
Yes, sir. Yes, sir.
So I will, those things we will be discussing. So it would be up to RTD, whatever. Mostly it would be on whatever we said about uh, static and dynamic characteristics, measurement systems, etc. Now, before starting the tutorial, I will be first take first 10 minutes to complete the thermistor discussions and thermistor first. Then we will be area. So, for the thermistor, we have explained the thermistors mostly. It's an used is NTC thermistor, and the characteristics is temperature versus resistance of thermistor is some sort of inversely changing inversely like this there. So, and these are all metal oxides. They have got the advantage is that they are fast, very small size, but the major disadvantage is the non-linearity in the characteristics. So, as I told that always whenever we discuss about any sensor characteristics and etc., we always look for that, okay, the whether the characteristics is linear or not, and how to linearize the characteristics. So definitely, first thing is that the thermistor has got a very highly nonlinear characteristics compared to RTD. So naturally, linearity is more important. There are, and if we recall, the thermistor characteristics is given by RT is equal to, we call it RT0 e to the power beta into 1 by, okay, I'll put it in this way, 1 by uh, T minus 1 by T0. And here normally where is the RT0 is the resistance at T0 Kelvin. So the temperature is always, temperature T is already the temperature in Kelvin, and beta is a constant of the thermostat. We have told that mostly the beta approximately around 4000 is the T. So if we plot it, we will get a something like this. Now the question is that how to linearize this one. So if we put these things there for linearization, first of all, let us try to put it, say, suppose let T is equal to T0 plus of delta T. So in that case, I can say that for before coming to that one, RT0 plus delta T is equal to e to the power, is equal to RT0 into e to the power beta into 1 by T0 plus delta T minus 1 by T0. So this one we can express it as is equal to approximately, because here it is RT0 into e to the power beta into T0 plus delta T into T0, and here it is minus of delta T. So we can say that this is approximately equal to RT0 into e to the power minus beta delta T by T0 square. Okay? Is equal to minus beta delta T by T0 square. So this one I can define as is equal to RT0 into e to the power minus x. Okay? E to the power minus x, where x is equal to beta T0 by T0 square. And we know that e to the power minus x is equal to, I can expand it, if we, if I am doing anything, any mistake, please correct me. This is by Taylor series, we can say. So what we can say, this is the linearity, the x term which is changing with linearly with x. This is what we call it the first non-linearity coming into it, x square by 2. Next is the x cube by 3 and factorial 3. In this way, the linearity, the non-linearity is coming up like this. So our linearization means our job is to try to reduce as much as possible these coefficients of x square, x cube, and etc. Then definitely the linearity will improve. So first technique for this linearization is that first technique is that using a parallel resistance. So that means, say suppose we have this RT, which is a thermistor, in parallel with, I put it RC there. That is some constant resistance there. So what we can say is that R equivalent is equal to RT RC divided by RT plus of RC. Okay. So in this case, if we can show it, that is a dr equivalent by dt. That means with time, with temperature, how this R equivalent is changing. If we take the derivative of this term with respect to uh, the temperature, by simplify, we get that RC divided by RT plus RC whole square into dRT by dt. Okay. dRT by dt. That means what we can say is that is that with respect to the temperature, what is it like this? That's because RC divided by RC plus RT is always less than 1. So what we can say is that dReq by dt is less than dRt by dt. So first thing is that we can say that definitely if I put a constant resistance, the sensitivity of this one, the equivalent one, would be reduced. So as a result, what we can say is that this is your R equivalent. The sensitivity definitely it would be reduced because this is a parallel combination of this one. Intuitively, I can say that sensitivity is reducing, but so naturally the nonlinearity will also reduce. So we can say that the sensitivity is reducing. As a result, the nonlinearity will also be reduced. But definitely that may not be very convincing for you. So, so I would take recourse of another way to explain this one. So what we can say for explaining and convincing you that really the parallel combination, the nonlinearity term, ultimately whatever the nonlinearity we want to place, it should be in terms of this sort of series expansion. So what we can say is that, say suppose I put it, this is a parallel combination. So here let RC is equal to RT. I just put two, rather not RT, I will call it RT0. We have seen that this is RT0. So there are two parallel resistances. One is the R thermistor and one is RT0. And we have, say this one, we can say it is RT0 e to the power minus x. If we say that T is equal to T0 plus of delta T, we have seen that this can be, that means the temperature variation, its increment is very small. I can express it as RT0 into e to the power minus x. So in that case, what will be the R equivalent? It will be RT0 into e to the power minus x into RT0 divided by RT0 into 1 plus e to the power minus x. Okay. Mind it, our objective is to establish that really the nonlinearity decreases. And so we can say this is equal to RT0, and here e to the power minus x, I bring it to the denominator and then simplify it. I call it, it is 1 plus e to the power x to the power minus 1. Do you agree? So I can write it this one. So this I can say is equal to, from our earlier expressions, I can say it is this one, 2 minus x plus of x square by 2 minus of x cube by, I think this was minus, minus of x cube by factorial 3, etc. And this should be inverse. Is it okay? Now, you can do the simple hand calculation. Divide this one by divide this one by 1. That means simply 1 divided by 2 minus x plus of x square by 2 minus x cube by factorial 3, like this. Similarly, if we do it in this way, like this, you can say it is 1. So here you will have to write it down as half. Similarly, whatever we do it, interestingly, if we do it, we will find this R equivalent is equal to RT0 into half minus x by 4 plus of x cubed by 48 minus like this thing. So, what interesting thing, what we can see, what is the difference from this one there? I find that this x squared by 2 or x, the coefficient of x squared is completely equal to 0. So you can say the coefficient of x squared is 0. So naturally what is happening is that, and we will find that the third nonlinearity, cubic nonlinearity, the coefficient will also reduce. But anyway, I am not going into that one. What is interesting is that this x squared term, if we do the things there, you can simply try and check it, and this x squared term simply vanishes out. It gets cancelled out. So naturally, what we can say, the linearity improves. So that's the interesting thing of this thermistor characteristics, of this exponential characteristics, that by putting a parallel resistance, of course, we are sacrificing the sensitivity. In fact, we don't mind because thermistor is too high a sensitivity. It's very high sensitivity. Rather, we want the linearization that can be achieved by this one. Same way, this is what we calculate by method 1. That was a parallel resistance of this one. Next is another interesting method is also, I will be outlining it, but I would say try to do that one and be convinced yourself. So the other method of linearization using a Wheatstone bridge. What does it mean? I mean that use the thermistor in a Wheatstone bridge. You may ask, what is the advantage? I mean, how does it? Okay, we can use a Wheatstone bridge or like this there, but what is the advantage? How it can reduce the nonlinearity? If I recall, simply we have done this problem already. So suppose it's a linear resistance R into 1 plus X, and this is your capital E, and this voltage is small R0, R, like this there. Then we have seen that the X versus E0 by E, if we make it 0 to 1 or 2, it should be like this. We have seen that even though the resistance is linearly varying, but the bridge output is nonlinear if the resistance variation is large. Okay, that gives you, okay, we know that one, but also that gives you a clue, okay, of incorporating a nice idea there. Okay, the bridge is nonlinear if X is large. And I know the thermistor has got two things there. It is highly nonlinear And so the change, and also it's highly sensitive, X is also large here. So can it be done that this nonlinearity of the thermistor and the nonlinearity of the bridge gets cancelled out? If it is, definitely the characteristics will be linear. So that is what is done, and that's a nice way of bridge, the thermistor non-linearization is that you incorporate one thermistor in one arm of the bridge, and the bridge nonlinearity and the thermistor nonlinearity characteristics will cancel each other, and then it would be like this. So I just put it in this way. I am not going details of it, but I can say that so if it is a thermistor, let this is your R thermistor there. And I just put it all of the, so RT, I put it as R of 0 e to the power minus x. Instead of T0, writing it again, e to the power minus x, I can put it. And let all of them be R0, R0, and like this. So, in that case, E0 by capital E is equal to, here it is R0 e to the power minus x divided by R0 plus of R0 e to the power minus x minus half. And so simplifying it, it will get it is e to the power minus x minus 1 divided by 2 into e to the power minus x plus 1. And believe me, if we, and also I will request you try yourself and be convinced. In a similar way, you just expand it and divide by this, you will get a interesting result. It is minus of half of x minus of x cubed by 24 plus etc. etc. So here also the coefficient of x square term is not there. That means the first nonlinearity, which is the coefficient of x square, is vanishing by this one, which makes it really interesting that the bridge nonlinearity and the thermistor nonlinearity gets cancelled out, and we can improve the linearization of this one. So I will stop here about the thermistor. If you have any question, I can discuss. But before that, I will conclude that the thermistor is a good one. But only thing is that it is too sensitive, and the thermistors are not very replaceable. That is one problem, because they are two identical thermistors do not have identical characteristics. This is a problem of this one. Is it clear up to this? If we have any question, I can further clarify it, but I request you to try yourself and solve them and uh, do the calculations which you have skipped and be convinced here. So with this one, I'll stop about thermistor. Next day, I'll go to a different topic. But we can solve some problems on the tutorial. I think tutorial 2 I have already given. Of course, tutorial 3 I have not given it yet. Maybe I give it to ask you to solve within 2 or 3 days, 1 or 2 days. But any problem about the difficulty in solving any problem of tutorial 2? Some of them have given directly taken from Bentley. So Bentley's book would also be useful for solving it. Any problem for you? Did you face any problem for solving tutorial 2? Have you submitted tutorial, all of you submitted tutorial 2 problem?
Yes, sir.
So You didn't face any problem, Saurabh? Okay.
No, sir.
So if it is, then you could have discussed, you can tell me, then I will not go further about the tutorial 2. I hope you have understood it and these things here. So I would rather work out one or two examples on the bridge linearization using RTT. Suppose I have a circuit like this. Say, suppose, okay, at this point I can put to an amplifier, instrumentation amplifier of gain of K. So can you find out what is the value of V0 in terms of this temperature? So I claim definitely you are clear about my intention that it will make it linear. Why? Let us try to work out. Let's try for 2 minutes or 3 minutes. Then if it is difficult, we will be clear. Let's try it yourself. Then I would be solving if you are not. So what is to be seen that two identical RTDs are used, rather it is not common unlike this, and that too to be used in opposite arm. That too used in opposite arm, and both of them are measuring the temperature. Okay? Angana, do you have any difficulty or on this solving the problem? Did you try to solve the problems? Yes, I am speaking to Angana Mondol. Is she listening? I hope. Anyway, uh, what is your opinion about the problem? Vishal Verma or Saurabh Mishra? Anybody can speak? How to solve the problem? Anybody? Any clue to start with? Okay, if nobody is responding, I would solve this one, but don't think that the tutorial class is only solving some and doing some worked out example, but still I would say it. So what is the voltage here? It is Vref. And so there is a negative feedback circuit there in the op amp, and I assume the op amp is to be ideal. So what is the voltage here? It is also Vref. So naturally, what is the current flowing it? I is equal to Vref divided by R1. So it is interesting to see in an under ideal op amp conditions, this current I is independent of the feedback resistance or whatever be the configuration. And since it is an ideal one, so the thing is that this same current is ultimately going back to this one because no current is flowing to the inverting terminal of the op amp. So op amp is delivering the current I and this is going to the ground. I is equal to V reference part. Now look at this circuit, this bridge. Look at this bridge. So what we have is that you see this is one path, another is this path. So the current I is divided into two parts, and obviously this instrumentation amplifier does not draw any current. It is some voltage which just amplifies. And interestingly, both the path have got identical resistance, whatever be the temperature. So I say naturally the current will be divided into two identical halves, I by 2 and I by 2. So that's all. The current would be divided by I by 2 and I by 2. So we have I is equal to V reference by R1. So basically it is this bridge is driven by a constant current source. This bridge is driven by a constant current source. And this and also the bridge two resistance paths are basically identical. So the current is divided into two parts there. So E0, I can say it is equal to I by 2 into R into 1 plus alpha t minus R. So this is this voltage minus this voltage. So here it is I by 2 into R into alpha t. And what is I by 2? It is V reference divided by R1 into R into alpha, sorry, 2R1 into R into alpha t. So, it is simply proportional, though we are using bridge and all the things there, whatever be the alpha t, whatever be the temperature, this is a one scheme for bridge linearization that will give you directly proportional to the voltage, proportional to the temperature. Is it clear? Any question? But definitely it is assuming that the op amps are identical. Any question? So, lastly, I would be giving you another problem and just give you some outline of to solve it. But definitely, this is only to help you, but you must try problems. Bentley's problem, and as I told, there are many other books, particularly Franco, I told it, and some analog electronics there, as well as the Palasereni's book. There are many for this bridge linearization circuit. Next example I will give an outline of this one is that this is also another design example. Simply a potential divider, a resistance 5 volt and an RTD is there, and it is amplified by a resistance R2 by R1, but a voltage reference voltage is given for a particular purpose. What we can say is that the this RTD is R at 0 degree Celsius is equal to 1000 ohm. Its platinum is a 0.00392 per degree Celsius. It's alpha at 0. And the current limitation of this one, I should be, this is the current I, should be less than equal to 50 microampere. Because if it is more, then I have seen that first of all, that will cause the self-heating error. Also, the current mode, it may burn out also. So always for protection, we keep it, because once you see any resistance or element like this, we say 100 ohm 1 watt or 100 ohm 10 watt like this. So this power requirement, power is constraint is always given, or we can put it in terms of maximum current it can go for it. And what is requirement is that find V reference and R2, R1. That means that it is a design problem, it could also say. So that at T is equal to 0 degrees Celsius, V0 is equal to 0 volt and T is equal to 50 degrees Celsius, V0 is equal to 2.0. So basically, otherwise it was fine, but I want in is such if it is a potential divided, I want get 0 voltage at 0 degrees Celsius. To achieve that one, I have used a reference voltage. I connected a reference voltage in series, and so that it can compensate or cause an offset so that the voltage is 0 volt at 0 degrees Celsius. And also I want that at 50 degrees Celsius, this output voltage should be 2 volts. So basically, what is the R2 by R1 or these things we be we want to design and like this thing. Okay? So we can say that the similar way R of 0, this is an RT. So RT at 0 degrees Celsius, it is 1000 ohm, and RT at 50 degrees Celsius, please check it, it is 1000 into 1 plus 0.00392 into 50. Please check it. According to my calculation, it comes to be, what is it? It is 1196 ohm. Okay. And also, what we choose, the value of R we need to choose. So, what is the value of R we need to choose? That this I is equal to 5 divided by R plus RT. So maximum current would be is less than 50 microampere. So what we can say that it is 1000 plus of R should be is equal to, okay, at the extreme end we can say it is equal to 5 divided by 50 into 10 to the power minus 6. So that is the limiting value there. And so it is 10 to the power 5 ohm. So we can say 10 to the power 5 means 100 K. Okay, we can say that choose I is equal to, sorry, R is equal to 100 kilo. So we can ensure that always for all the temperatures, this will not never go beyond 100 there, 50 microampere. Now it is the rest is very simple. Once we have it, we know that this is voltage is, say suppose this voltage is E. So this voltage should also be E because it's an ideal op amp. So what we can say is that V reference minus E divided by R1 is equal to E minus V0 by R2. And we have got from these expressions, we can say that minus V reference, you can check it, uh, plus of E into 1 plus of R1 by R2 is equal to R1 by R2 into V0. Just you can simply write it down. And from that one we have it that for E is equal to, what is the value? One case at 0 degree Celsius, what is the value of E? E is equal to, I am just giving the value, 49.5 millivolt. That means at 0 degree Celsius, what is the value there? At 50 degrees Celsius, here it is E is equal to, it comes to be is equal to 59.1 millivolt. And what we require is that correspondingly, what is your V0 is equal to 0 volt, and what is your V0 is equal to 2.0. So, solving, you can, what are the unknowns? One is that V ref and another is R1 by R2 or R2 by R1. So these two unknowns, two equations, by solving it, please check it. I make many mistakes also. So please check it uh, that you arrive at and correct me. Uh, so by solving we get it, according to my calculation, V ref is equal to 293.66 millivolt, and R2 by R1 is equal to 207. Please check it. So accordingly R1 and R2 we can choose it, and we can design the circuit in this manner. So mostly once you understand the very basic schemes and etc., they are working of this one. The rest of the things are mostly solving Kirchhoff's law and nothing else. So we can solve it. But there are certain times some tricks are there. You must look into the circuit and try to understand how to solve and how to approach it. So with this I will stop here, and if you have any further, please try the problems. I will try to give you some problems if possible also for to work out. But as I told, that Palasarin's book as well as the Franco's book, a number of bridge and also a number of bridge linearization circuits with op amps are also there. And obviously Bentley's book, you can see many other problems. So I stop here. If there is any question, I am ready to answer. Yes? Any question? Saurabh, is it all right?
Yes, sir.
Okay. Ajay Ram Meena,
Yes, sir.
any question, any doubt you have?
No, sir.
Please try to solve the problems. Huh? And
Okay, sir.
okay then. Thank you. Let's call it a day. Call it a day. So on Monday we'll take up some new way, and Tuesday some almost 1 hour way to test would be there. I will be giving it and telling it. It would be all the details would be given on Monday, by Monday, alright. So it would be a mixture of problems as well as some short questions. Right.
So
Okay.
please provide some extra problems as well.
Pardon?
Sir, some extra problems, sir, for practice for the test.
For practice, yeah. I have already given. So you try to find out, and I believe that if we understand the basic concepts, any unknown problem you will be able to solve. So that's the conception is important. Try to do that one, and then, okay.